Okay, today, section 15.1 and 2 of the book. Oh my gosh. I don't think I've ever made that mistake before. I just went 12, 12. Oh, it'd be cool if it was 12, 12, 12.
We're in the future. We'd be dead.
I'm actually planning on showing this on 12, 12, 12. All right. We're going to talk about simple harmonic motion. Simple harmonic motion, specifically for a mass spring system. And this is really some very cool stuff. I really like simple harmonic motion. It's a topic that's used a lot in all scales of physics, from the atom, all the way out to big things that are, anything that can vibrate back and forth involves simple harmonic motion, or you can use simple harmonic motion to model it. And so the easiest way to do it is by starting off with the mass spring system to introduce it. There are other systems that turn out to have what we call simple harmonic motion. And basically, when I say simple harmonic motion, it's the motion of a sine wave or a cosine wave, a sinusoidal wave. If something moves through space with a displacement, function that makes a sine wave or a cosine wave, it's simple harmonic motion. And that's going to turn out to be true for a mass spring system. So let's come up with this ideal system. Here's a frictionless surface like this, and here's a spring. Whoops, that's all right. So here's a spring, and it has a spring constant of K. Remember what the spring constant means. It's how many newtons of force you need to stretch it 1 meter or compress it by 1 meter. And again, that's a ratio. So most springs you can only compress a few centimeters, or whatever, but you can still put that in terms of meters. Now, here's our mass. Let's put it on wheels just to really emphasize that there's no friction here and it has a certain mass. Now, let's say I've drawn it right here is 0. And what this means is that when the little mass on wheels here with our spring is at this location, there's no net force on it. That is, the spring is neither stretched or compressed. It's not applying any force to the mass at all. Okay? But if I stretch that guy out, let's say I put it out here. So now the spring is stretched way out here, and we'll call this this is some value of x. Well, we studied this before when we talked about Hooke's law. So Hooke's law, it says, look, this spring is going to pull it to the left. So my displacement was to the right, but the net force is to the left. And the amount of force applied by the spring is dependent on how big this x is, right? If I double this x, if I pull this way out here, the spring will apply twice as much force. Now, if I put the mass over here, a little bit closer, now I'm just compressing the spring, and so the x is negative in a negative direction. This would be negative x over here, but the force of the spring on the mass is now to the right. It's positive. And so if I draw a free body diagram of this guy, let's just put it right next to it, right over here. We've got gravity, and we've got this normal force. We don't care about those, except to say that they cancel each other out. But we do have this force of the spring. And this is the net force. So we can say that the force of the spring is the net force. It's equal to MA. But its value is equal to, the force of the spring is, it's negative kx, right? Okay, so the spring is going to give me a net force to the left if my position is to the right of the equilibrium position. And vice versa. If I had a negative x, well, the negative would cancel with this negative, and it would be a positive force, and positive means to the right. So this tells me something about the motion of this guy. And let's solve for A. A is equal to negative k over m times x. Now, k is a spring constant. It doesn't change with time. And mass doesn't change with time. Right? The thing is, so here's what we've got. The acceleration is directly proportional to the position, but in the opposite direction. Now, what we're going to show here in a minute, that whenever you have that situation where the acceleration depends on the position, but in the opposite direction, I'm going to end up with what we call simple harmonic motion. And here's one thing I want you to see. What is acceleration? Well, acceleration is dv dt, correct? And so the velocity, but what is velocity? Velocity is dx dt. So we can say acceleration is the second derivative, the second time derivative of position. So I can rewrite this equation using that. I can say d squared x dt squared is equal to negative k over m times x for a mass spring system. But in general, let's generalize this. If the second derivative of a variable is directly proportional to the variable with the opposite sign times some constant, you've got what we call simple harmonic motion. Now let's take a look at this qualitatively before we dive into the math and the differential equation. Remember, this is a differential equation. This is called a differential equation. And what we're going to do is we're going to look at a solution to this differential equation. In other words, what equation for x will obey this equation here? And that's what we're going to do next. But before we get to that, let's think about what's going on here. If I were to graph the position of this guy as a function of time. So let this be position and this is time. Okay. Now let's start here at the maximum position away, right? So at t equals 0, we're going to start right here. So let's let this, see, this is the x direction on here, but I'm going to represent it graphically by turning it over and making this the x direction. And then graph the position as a function of time. And one thing we can say is, look, immediately when I let go of this thing at t equals 0, this thing's going to be pulled to the left, and it's going to, but at first it's not moving, so it has a 0 slope, but then it's going to start moving towards the origin, towards the origin, towards the origin. Now, as it's pulling, it's getting faster and faster and faster, isn't it? Until it reaches its maximum speed at 0. So here's at x equals 0. So x will be 0 and will be at some maximum slope, like this. And then, but then as this mass goes past 0, this spring starts pushing on it and starts slowing it down, doesn't it? The spring's going to try to start slowing it down. And so the slope's going to get less and less and less until it reaches some, maximum value over here. Well, what we're going to show is that the distance from here to here is the same as the distance from here to here, where it's going to stop. So it's going to come to a stop, which means it has zero slope. And then the spring is going to is still pushing it to the right, but now instead of slowing it down, it's speeding it up until it goes back to the equilibrium position, and now the spring starts to slow it down again, and then it starts all over again. Right? Starts all over again. Now I look at this and I think to myself, just qualitatively, what does this look like? Yeah, actually, more specific, it's a sinusoidal wave. It's what starts at the maximum position? Cosine. So what we're going to do next is we're going to show that it is a cosine wave, and we're going to prove it by taking the derivative of it. So we'll do that next.